Hi, welcome back. It's good to see you again. Here's the next presentation on our introduction to calculus. Do you remember, here we are, the journey so far, how far we've travelled? Well, here we are. It was a Newtonian approach to calculus where there was a displacement time graph, distance travelled versus time taken, and we could quite easily work out the velocity, and we're assuming there, and we'll talk about this a bit later on, that the body of the motion is in a straight line. So it is velocity, which has that component of direction. But then, this was Newton's dilemma, wasn't it? Newton's dilemma here. And that was, hey, what if, two M's there, what if the displacement time plot was curved, a curved line here? There isn't a constant velocity now. The velocity is changing at all points along this curve. You see, I've drawn little tangents in there because that's where we're going. Because Newton said, hey, I'll work this out. If I want the instantaneous velocity or rate of change of displacement with time at a point, then what I need to do is to bring these points along the curve closer to actually what's happening. Decrease the gap between the curve and the chord there. And we're calling these lines joining 2 points on the actual displacement time graph as a chord. In Pearson's, and we'll look at that in a minute, they call this a secant, which is okay as well. So that was his problem. Can I work out the instantaneous velocity by taking points closer and closer to the point I'm interested in, point A? And then do you remember we said that, okay, well, let's draw the limiting position of that, which is back over here, was the tangent. Newton concluded that the limiting position of that chord was tangency. So we decided we would construct a tangent in here and work out its slope, and that would be V inst, the instantaneous rate of change of displacement with time. Okay, do you remember that? And then we said, hey, that's not too accurate, this construction type idea. Can we do it theoretically? And so we had a chord here, and we said if we're at a point, x is 1 and y is x squared, so y would be 1 squared, be 1, and we moved out a little bit to 1 plus h, and the y value would be 1 plus h squared. Let's look at the behaviour of the slope of that chord as h tended to naught, and we did a theoretical calculation. So that's what we're on about in this next presentation. Can we actually do an accurate calculation for the slope of the tangent? And this is called, back up here, finding the derivative, deriving, if you like, a function which will give us the slope of the tangent. So we're going to be doing quite a bit of algebra. Okay, and that was the formal final point of the thinking of both Newton and Leibniz. Leibniz wasn't so much based on displacement and time over here, but in general, with the rate of change of any function y with respect to variable x. Now, just before we go, I want you to be critical of the screen, and please don't say, well, I don't like all your scribblings there, Huddy. But mathematically, there is one error repeated twice on this screen, and it came up in the last presentation. Can you see it? Have a quick look round. What is the error that I've left there on the screen? Okay, did you get it? Yep. Well, it's no units here. Time, we said, should be listed in units, and no units here. What did we say? Well, could you all at meters? And down here as well. Okay, so please take that point. I've left it there to see if you could spot it. When you do a graph, you must have labelled axes, good scale, and units, all those things. All right, let's get underway now and say, can we do this for any function? Will we be able to find its instantaneous rate of change no matter what the formula for the function is? Come on down and let's look at the mathematics that Newton and Leibniz both arrived at there. Differentiating from first principles. What does that mean? We're going back to the first principles here that both those guys came to a conclusion of. And here, differentiating, finding the difference between. What are we finding the difference between? I think it's the rate of change of the function at different points. Differentiating, finding the difference. That's one way of looking at that word differentiating. Differentiating between points on the curve according to the rate of change. Okay, so come over here. We've got two approaches here. Finding the rate of change of one variable with respect to another, and that was with Newton very much based on the rate of change of displacement with time, velocity type problems, and then with Leibniz finding the slopes of tangents to curves. Okay, and they're the same thing, of course, because we said the instantaneous rate of change was equal to the slope of the tangent to the curve. It's the limiting position of this chord or secant, as Pearson's refer to it. We'll be taking screen clippings from Pearson shortly. So that's why I'm overlapping there. So let's look at this. I've got in general here a diagram for any function y equals f of x. And I'm going to take any point on it, call it x, and when I sub in to get the y into the function, I'll have x, f of x. Then I'm going to take a point further out, which is a bit further out, so it's out further by h. Here it is here. We've gone across in x land by a further h. So the x coordinate of this point q is x plus h, and the y value of this point q, sub it into the function. Remember, that's a common idea. The function expression, it gives you the value of the y coordinate for a given x coordinate. So this is all in general from first principles, not dependent upon any particular function, but something that we want to be able to do for every function. Find its rate of change at an instant in time, or an instant, a point, an x value on the curve. Alright, so what's the y step? Or let's come up, we've had this delta symbol now. Delta y means, Greek capital delta, means change in. So instead of y step, let's make it delta y. What would it be? This y minus this one. Oh yeah, f of x plus h, take f of s. And what is the delta x? The x step will just be h, because we've gone h further out. What are we trying to do? We're trying to find the slope of the tangent, and that's going to be the limit as h tends to naught of the slope of the chord, which is the y step over the x step. Now, if we could do that for any function, no matter what f was, then we would be able to find the slope of the tangent, which is equal to the instantaneous rate of change. So there is a dichotomy there, a twofoldness. Come back up here. These two I want you to see as interactive. One implies the other. Okay, find the rate of change of one variable with respect to another, or find the slope of the tangent, means the same thing. It's down here. Here's our first principles definition. If they ask us for this, find the slope of the tangent from first principles, or the rate of change, we must use this expression, the general first principles idea. This process is called differentiating. Differentiating between points on the curve as to what their rate of change is, of how quickly y is changing with respect to x. Let's come down and see some of this in action here. So here's Pearson's definition: slope or gradient of a curve at a point. Slope of the curve we can call the slope of its tangent, and is given by slope of the tangent, limit as h tends to naught of slope of the secant. We're calling this a chord. Can use either word. There's a limit as h tends to naught of the general, this is the general slope of a line joining any 2 points on the curve, which is the slope of a chord. If that exists, if we can find that, then we've found the slope of the tangent, or the instantaneous rate of change. Okay, let's have a look at an example here from Pearson's now. Screen clippings from Pearson's here, and we'll just bring this whole example up. There it is. Find a rule for the slopes of the tangent lines to the graph of f of x equals x squared plus 1. Use this rule to find the exact slope of the curve at the pointers 0 and at 1. So if we do it from first principles, that should be written there, first principles, because we will learn quick rules for doing this later on in this presentation. So first of all, if we let f of x be any point on the graph, then here's our fundamental definition. The slope of the tangent is the limit as h tends to 0 as we bring that point closer to our target point along the curve of f of x plus h minus f of x over h. Let's do it for our particular f. That means we've got to put x plus h in our function. Where's our function? Up here. So it's x plus h squared plus 1. Minus put f of x in there. Well, f of x is x squared plus 1. So this thing here is f of x plus h. Take f of x. Let's see if we expand it, first term squared plus twice the product plus the second term squared, and you've got the 1. Take away f of x, then we get no x squared term, 2xh plus h squared, and no 1s are left. So coming down here, we've got cancelling, provided that h is not equal to 0, you can cancel, and therefore you get the limit of this function, which itself is not defined at h is equal to 0, but we did this in the last presentation. It can still have a limit as h tends to 0, even though it's got a hole in it, it's discontinuous at that point, can still have a limit, can't it? And therefore, as h tends to 0, the limit is 2x. Wow! What have we done? Let's have a look at it. We still haven't answered part B, so in part B, what that means is, if we stick x as 0 in here, the slope is 2 times 0 is 0. And look, let's look over here, When x is 0, the point is 1, because the function is x squared plus 1, so stick 0 in place of x squared, you get 1. So it's a point 0 at 1. And why is the tangent got slope equal to 0? Oh, because it turns around there and we've got the vertex there. Now this might be useful later on. And you expect it to be a horizontal line with a slope of 0, because it's just touching across the bottom of the parabola there. It is a convex or concave up parabola. What about where x is 1? Stick 1 back up in here. 2 times 1 is 2. And looking at this, does it make visual sense? Well, let's look at x is 1. Here it is here. Y would be 1 squared plus 1 would be 2. And here's the slope, and the slope is much steeper. It equals 2. Wow! What a process. If we do this for any function and we come up with this answer as to the limit as h tends to 0 of the slope of that chord, we now have a powerful, what do we call it? It's a derived function. And it's derived from the original function, and it will enable us to find the value of the tangent, slope of the tangent at any point. A derived function, sometimes called the derivative. Okay, and that's the subject of this presentation. To find this function, derive it, find the derivative, which will give us the slope of the tangent of the tangent to the curve at any point. Alright, are you getting the hang of it? Let's go on and have a look at a bit of a summary here from Pearson's. The derivative and differentiation. The derivative, and we're going to give it a symbol now. Not m of the tangent, we're going to give it f dash x. So this is called the derived function. So we're going to use this symbol. F dash x is the derived function, or the derivative, and that's going to give us the slope of the tangent in there. Okay, and instead of putting m of tan, we're going to call f dash x. F dash x it's called. Okay, we might just put that with, say, f dash x. F dash x for f of x. And here is how we did it. We've got to do it that way if they say from first principles. This process of doing this is called differentiation when we do this. We're differentiating between the rates of change along points on the curve. Now, if it exists everywhere, it's a smooth curve. That's not actually part of the IB course to know that. The process of finding the derivative is called differentiation. We've talked about that. If y equals f of x, then f dash s is a formula for the instantaneous rate of change, because we know that's equivalent to the slope of the tangent. This was Newton and Leibniz's conclusion there. If we want the instantaneous rate of change, we want the slope of the tangent at a point. Okay, so we're getting some language in here and some notation to make it neater. Okay, and that's good mathematical language now. Okay, let's go down and have a look at a little bit more of a development here. Not much more to do. If finding the derivative of a function, the derived function, is indicated, if functions like that, then we denote the derivative as f dash x. However, what about if the function is called y equals x squared plus 1? We could use y dashed of x for the derivative, which would be 2x, as from before. Different notation. You can call it y prime. We usually call it y dashed, but y prime is technically more accurate. The notation, what's this? Derivative of y with respect to x. That's what that one is called. We call this also dy by dx. It's not a fraction. Where do you think that comes from? Okay, dy by dx would be 2x. They're all different symbols. Here they are, y dashed and f dashed x are all different symbols for the same thing. The derived function will give you the slope of the tangent. What might this come from? Their clue is d. Hey, I talked about d earlier. What if we called it the Greek d, delta? That's where it comes from. Okay, because dy by dx is the limit as delta x tends to naught of delta y on delta x. Let's just do that. Let's tidy that up a bit so you can see a bit more. Pearsons don't actually unpack this so much. But if I wanted to find the slope of that chord from there to there, that would be change in y over change in x. So my slope of the tangent, which my derived function f dash x or y dash x, would be the limit as the y step tended to naught. So we're going to move along here down of the change in y over the change in x. Y step and over x step. So that's the origin of that dy by dx. It is not a fraction. It's all this. It's the limit of that slope of the chord. Okay, so what do we got? Let's make a little summary here. We said it's called f dashed x, or it can be called y dashed, or it can be called dy by dx. All symbols for finding the derivative or the derived function, which will give us the slope of the tangent to the chord, a tangent to the curve at any point, or the instantaneous rate of change. Okay, that's a lot of work to do that for every function, isn't it? Let's have a look here. Let's do another one. What about x cubed? Okay, we start with our definition, always, then put x plus h in our function. So it'll be x plus h cubed, take x cubed. Now we need to expand this. Now they've done it the very long way here, but you should be able to go from here to here with the binomial expansion. Do you remember that from earlier work? This connection is explicitly mentioned in the IB course. Remember that? Pascal's triangle, or the C notation, C3 C31, C32, C33. Should be able to get these terms that way. and then take off x cubed. What do we notice? They go out, factorising the h, and then this will cancel, provided that h is not equal to naught. Just talking about the limit as we approach that. Then if we sub naught in here, that'll go to naught, so we'll be left with 3x squared. Therefore the derivative of x cubed is 3x squared. Let's come down and use it now, just over here. Here's our function, x cubed. And if we say, let's go to the point 1, 1, let's put x as 1 in our derivative, our derived function. Slope would be 3. Let's just go back up there, slip a bit there, the slope would be 3. And if we put in neg 1 into our function here, into our slope giving function, neg 1 squared is 1, and that would be 3 as well. They've both got a slope of 3. That's starting to make sense, isn't it? It's very, very handy like that. Okay, let's come down now and have a look at another example. Now, what about x squared plus 1? Okay, if we were to draw x squared and x squared plus 1, one moves up a little bit from the other, doesn't it? It's a y translation or a vertical translation of plus 1, and there it is there. So the tangent at 1, 1 on x squared is the same as a tangent at 1, 2. Oh, it looks like both of their derivatives are the same, 2x. Okay, because 2 times 1 is a slope of 2, and here is a slope of 2. You can see geometrically why that should be the case. They both have a common derivative, or function which gives the slope of the tangent or the instantaneous rate of change. Alright, are you enjoying it here? Let's keep going and derive a little bit more of the theory here. Hey, so I guess your next question is, can technology help me with this? And the answer is, of course, it can. Here's the Casio 9860 Plus graphics display calculator, and let's come over to this window here. I've got a lot of garbage still on there. This is in run mode, and you can see with this little square here that I've got it in math mode there. Okay, so it's actually running in math mode. And when it's in this mode here, just do that again, what we can do is to go to options, so hit options in there, and we get this window, and if we hit we'll choose calc and hit F4, we get these options here, and there it is, d by dx. So if we choose F2, then we come up with this window, and it's asking us to put into this hole here the function whose derivative we want. And here it is here. Let's put in there x squared at x is equal to 2. And we get the answer over here of 4. So the graphics display calculator, this one's Casio, but the others will do it as well. Pearson's will show you the TI, and you can actually evaluate the slope of the tangent, or remember the instantaneous rate of change, both of those things, instantaneous rate of change at any point. Okay, so remember that, that's in math mode. Let's come down and look at it in two other ways. So coming down here, let's go to Shift Menu to go to Setup, and it's in math mode, but if we hit F2, we'll choose linear mode. And if we choose linear mode and then hit options, we get the window again, and if we choose F2, we get a different appearance now here in the linear form of run mode, we get this. And you have to know the syntax. You put in x squared, comma, the number that you want the derivative of x squared to be evaluated at. And if you'd execute, then you would get 4 again. So in linear form or math form of run mode, you can do it, remembering down here to hit options and then choose the derivative. D by dx is the notation used by the calculator. Okay, one more way of getting the calculator to help out here, and that's to draw the graph. Okay, so we go to graph mode, enter the function x squared, and then we have to go to shift menu, which is set up, and make sure we get this window and see it here, derivative on. So scroll down to that and make sure the derivative is on. It doesn't matter whether this is linear or math mode there for this. What we need is derivative on. So it's shift menu to set up, make sure the derivative's on, draw the graph, and then down here, the next window, come down here, you hit shift and F1, which is trace. See it in there, trace, and you pop on there, and it will give you at x is 5 or any x value, we can enter one in a minute, x is 5, y is 25, and the derivative of that point is 10, which means it's got a very steep tangent. Just remember what we're doing here. Delta y on delta x would be the limit of that, would be the slope of this tangent, which would come to 10. Delta y and delta x at that point of tangency would be 10. Then we could enter a different x value. X is 6, just hit 6, and it will give you the next one over here, this final window. X is 6, y is 36, because it's x squared, 6 is 36, and the derivative is 12. So it's following that rule that dy by dx for x squared is 2x. Okay, that's if we haven't worked that out for this function. It will do it for us, either in run mode, either math or linear form of run mode, or in graph form. Later on we'll see it will actually give you the equation of the tangent as well, but we'll come on to that a bit later on. At the moment we're looking at just finding the slope of the tangent, which it means the instantaneous rate of change at a point. So the calculator won't actually find this function. It will give you only the value at a specified x, okay, along that curve. Alright, you get it. We've got a bit of backup there now, so let's keep going and see what we think. Okay, let's do another example from Pearson's. Find from first principles. Now that's mandatory that we use this definition here. When they say first principles, we must use that definition. So what do? We put x plus h in place of x in the function. So here, instead of x squared, it's 3 times x plus h squared. Plus 2 times, instead of x, 2 times x plus h. Take the function, which is 3x squared plus 2x. Expanding all this out, first term squared, twice the product, second term squared, all times by 3, then 2x plus 2h, there it is all there. Then take away the function, and if you do that, the x squareds go out, the 2x goes out, and you're left with 6xh plus 3h squared plus 2h, all over h. And they've left out a step here. We could put in limits h tends to 0, h outside of 6x plus 3h plus 2, over h, and that will cancel, provided that h is not equal to 0. You're just looking at coming up to that point on the function, and you get this. As h tends to 0, that will go out. So the derivative will be 6x plus 2, which is either y dashed or dy by dx or f dashed x. You could have any of those in there for that first principles. So it says, if you want the slope of the tangent to this function here, right up the top here, if you want the slope of the tangent to that function at any x value, this is the way you get it. Put x equal to whatever value in there and find the slope of the tangent, or remember the instantaneous rate of change. Alright, come down a bit. What about this one? 1 on x. Oh, this is interesting. F of x plus h. Instead of x in there, you've got to put x plus h. So it's 1 over x plus h. Take the function 1 over x all over h. Now we get a common denominator, get them both over x by x plus h. You could think of cross multiplying. That's another way of thinking about it, to get this form. And then of course, if you simplify the top line, x take x plus h, x take x is nothing, neg h in the top line over x by x plus h over h. Okay, and so you could say this is 1 on h. They've gone to a bit of trouble here. I would have said just leave h in the bottom line there. Hang on, we don't need a bracket for x, I don't think. X by x plus h, like that, and then go to this line here. Okay, don't know what you want to do there. Right, there's a little bit of algebra there. So now we will cancel this, provided that h is not equal to 0, and therefore we've got neg 1 over this one, and so h tends to 0 means the derivative of this, that will be 0. X times 0 will be 0, will be neg 1 on x squared, so it'll be neg x to the neg 2 if you like. Okay, a bit more complicated that one, because you've got a quotient, what's called a quotient. Here it's a quotient function, or as we know, a rational function would be 4, or a reciprocal function 1 over. Okay, a bit of algebra there. Okay, let's go on and have a look at what we've found. Basic differentiation rules. When we do this process, when we differentiate or find the derivative, that is the function which is derived to give the slope of the tangent or the instantaneous rate of change, any of those, and there are the three symbols for them, aren't they? Okay, so if fx is x squared, derivative is 2x. If it's x squared plus 1, same derivative. We found that. They have parallel tangent at a certain point. 3x squared plus 2x, did we do that one? Yes, we got 6x plus 2. X cubed, we got 3x squared. X to the neg 1, we get that one. So, if we have f of x equals x, then the derivative is 1, since the line has a constant slope. Let's just draw that. Pearson's are saying here, if we had that function, y equals x, what's the slope of the tangent? Slope of the tangent is f dashed x, is the same as the slope of the line. The tangent's the same. Let's draw a few along there. So at f dashed x equals 1. Okay, f of x equals 1. So the slope has constant slope equal to 1. F dash x equals 1. If f of x equals 1, let's draw that one down here. F of x equals 1. That's a flat line there. Y equals 1, or f of x equals 1. All the tangents are coming along there. All are parallel to the x-axis, so they all have a slope of 0. Okay, so that's interesting. So that would be true whenever the function is a constant. If it ever goes parallel to the x-axis, so let's change this. If f of x equals a constant, it'll be a flat line job, and the slope of the tangent is 0. F of f dash x is 0. So they're saying this leads to our first basic rule of differentiation. Well, what is it? Let's see what they've come up with here. They're saying, can you see the pattern? The constant rule. Derivative of a constant function is 0. That is, given c is a real number and if f of x equals c, then the derivative is 0. And the idea of that is f of x equals c is a line like this through the value here 0c, and the slopes of all the tangents will be 0. F dash x will be parallel to the x-axis, will be 0. Okay, let's come down to a summary now from Pearson's to the next rule, and these results, can you see a pattern through these results? This is what we've found. If fx equals x to neg 1, f dash x is neg x to neg 2. If fx equals x to the naught, which is just 1, its derivative is 0. F of x equals x, its derivative is 1. If x equals x squared, its derivative is 2x. If x equals x cubed, oh, I think there is a pattern there, and that's what Pearson's have come up with here. If n is a rational number, that's a ratio of integers, a fraction or a whole number. If f of x is some power to that sort of power of x, then the derivative is nx n minus 1. Can you see it? Let's take this one. Its derivative, what happened to the power? It went in front, x to the 1 less power. What about this one? 2 went in front to the 1 less power. So that looks like, from inductive reasoning, that is from examples, that looks like a rule. In other words, if you have a power function, then the derivative is the power times x to the 1 less power, if you want to think about it in words, because that's a generic type of mathematical formula showing an overall pattern. Can we actually prove that? Because Pearson's don't do this, but I think it's worthwhile. It's not actually in the course, but let's try and do it. Let's go here now. F of x equals x to the n. Okay, not taking any particular examples like this. This is called inductive reasoning. Let's say now f dashed x is the limit as h tends to naught of f of x plus h. This is from first principles. Take f of x on n. Okay, let's keep going. It's a limit as h tends to naught, f of x plus h. So that'll be x plus h to the n. Take x to the n on n. Oh, do you remember your binomial expansions? This is binomial, isn't it? There are two terms. Let's do it. Limit as h tends to naught. Okay, let's expand this. This is c n naught. What? X to the n, h to the naught. Plus c n 1, x to the n take 1 by h to the 1. Plus c n 2, x to the n take 2 by h to the 2. And we keep going, don't we? We go down to c n n, no x, and h to the n. Take x to the n on end, on the end there. So that bracketed term is the binomial expansion of that first term there. Do you remember that? Okay, let's have a look at what we can do now. Let's simplify this. Limit as h tends to naught, cn naught, outside entries of the rows of Pascal's triangle. Cn naught is 1, no matter what n is. So it's x to the n plus cn1, x to the n take 1 by h plus cn2, x to the well, I think I made a mistake there. N take 2, I've left out the n take 2. N take 2 here by h to the 2 plus right up to c and n, h to the n, take x to the n, all over h. Now because this is 1 up here, that's x to the n, take x to the n, there are no x to the n's left. So this is limited, h tends to 0. Now all of these have an h in them. All of them right the way through. So let's put the h out the front. So this is c n 1, x to the n take 1, plus c n 2. Here x to the n take 2 by h, plus they've all got an h in them, c and n, h to the n take 1, if we factorise that h out. Okay, are you still with me? This is fairly hard, bit beyond standard level here. Okay, now we will cancel this with the proviso that h is not equal to 0. Okay, what have we got left? Limit as h tends to 0 of c n 1, x to the n take 1, plus c n 2, x to the n take 2 times h. They've all got h's in them, down to c n n, h to the n. Oops, shouldn't be n take 1 there. Up there it should have been just n, shouldn't it? C to the n. Okay, now, as h tends to 0, all these other terms have got 0 in them. That's 0, that's 0. So all of these, each one separately, is going to tend to 0. So this is the limit as h tends to 0 of cn1, x to the n take 1. Now, I don't know whether you know much about combinations. You're supposed to by now from the binomial expansion, but cn1 is always n. So this is x, n times x to the n take 1. Oh, I think we've just proven it. That's interesting. It's an interesting bit of algebra, and a crossover with the binomial expansion, where you've got two terms, some difference of two terms raised to a power, and you should know that. Now this is not required in the syllabus. I just think it's an interesting thing to do, to prove, to actually prove. Come back up here. Here we are, come back up here. If the function is that, we've just proven from first principles, not by inductive reasoning, not by seeing the patterns that we were doing up above there, but by actually doing the derivation algebraically. So if you're going on with maths, it's interesting to challenge yourself here to see if you can understand that expansion. Alright, let's come down now. Just before we go on, I want to summarise a bit. This is Huddy's favourite description of differential calculus. Here we go. I'm going to draw you a circle. I'm going to say up here, we've done the process of finding the derivative. That is, the derived function, which gives, watch this now, double arrow, the slope of the tangent. This was the idea of Newton and Leibniz. The rate of change, so limiting position of the chord around here to the instantaneous rate of change of the function at that point. It's a trichotomy. Each of them mean the same thing. You can find the derivative from first principles or a rule, but what does it mean? It means both of these things equally. It can mean the slope of the tangent to the curve at the point, which is equivalent to the limiting value of the slope of the chord, which is the instantaneous rate of change of the function at that point, v-inst in Newtonian terms. Do you get it? This is, to me, a very, very, very important diagram to remember. The interaction between what you're doing, the derivative up here, and the meaning of it. Okay, so try and hold on to that idea. We'll talk about that again later on. Okay, come down, let's do some and see what we think. Okay, the sum and difference rule. If you have two functions added or subtracted, the derived function is the sum of the derivative of the first plus the derivative of the second, or the difference. Now we can prove this from first principles, but Pearson's don't, and I'm not going to here because it's not actually within the course, but I will give you an example. If f of x, let's say, is x cubed plus x to the fifth, then the derivative is the derivative of the first one using the x to the n or power rule plus the derivative of the second one. And you can prove that from the fundamental first principles definition. What is that again? Remember, first principles definition is f dash x, so limit as h tends to naught, excuse me, of f of x plus h, take f of x over h. If you went through that definition with this general expression, g of x plus h of x, or g of x take h of x, you would be able to show that. Okay, so if you have a function which comprises two functions added, its derivative is the sum of the derivatives of those two functions. Okay, what about the constant multiple rule? If f of x is some constant times g of x, then the derivative of this function is that many lots, the constant times the derivative. And again, we can prove this using the rule. Not within the course. Let's take an example. If f of x equals 3 times x squared, the derivative then is 3 times the derivative of this function of 2x, which is 6x. So you can take a constant out the front and just worry about the function in x. Apply the rule just to that function in x and then have this many lots of it out the front. So do you get it? If you have a multiple, and there's the rule, the constant multiple rule, if you have a constant times a function, then it's the constant times the derivative of that function. As you would expect, the constant doesn't have any rate of change with respect to x. It's a constant. So it's just that many lots of the rate of change of the function in simple terms. Okay, let's keep building. Can you see what we're doing? I think it's summarised here, isn't it? We don't want to do first principles all the time. It's too hard. Can we adapt some rules? Let's have a look. The derivative of a constant is 0. Let's just check it graphically. A constant is like saying I have a function which is not varying, so it's going to be through here. F of x equals c. Its derivative is the slope of the tangent, and that will equal 0. All the tangents are parallel to the x-axis, have a slope of 0. Next rule, we just proved this one, is that. Here we can say that's any real number. Here it's got to be a rational number. We've only proven it for whole numbers or fractions. Then if we have the derivative of two functions added, it's the derivative of the first plus the derivative of the second. This dy by dx notation is more Leibniz notation, whereas the f dash x or y dash is more what Newton used. And here the last one, derivative of a constant times a function is the constant times the derivative of the function. And with any constant, which is any real number there. So rules. Rules are now will now replace the first principles definition, if we're allowed to. If they say from first principles, we must go back to using this whole thing and the algebra involved there. But otherwise, let's start finding the slope of the tangent or the instantaneous rate of change using our rules. Okay, come on down and let's practice some of that. Here's example 8 from Pearson's. For each function, find the derivative using the basic differentiation rules. Find the slope of the graph of the function at the indicated points. Use your calculator to confirm your answer. Okay, let's have a look. Here's the first function, and here are the 2 points at which we want to find the slope of the graph or the slope of the tangent. let's do the derivative of this. Oh, it's a biggie. There are actually 4 little functions added or subtracted. So it's a derivative of the first. You don't actually have to put this in. Plus the derivative of the second, minus, etc. Let's do it. Derivative of x cubed, 3x squared, using x to the n rule. 2 lots of the derivative of this is 2x. 15 lots of derivative of x is 1. Remember the derivative of x, dy by dx, is 1. Y equals x to the 1. dy by dx is 1 x to the naught, if you like, or just 1. Derivative of a constant is 0. So we can simplify it to that expression. And what that means is at these points here, slope of the curve at neg 323, put neg 3 in your derived function. There it is, in all the x holes. And you get 0. So in other words, when you draw the graph of this function, you should have a horizontal tangent with a slope of 0 at that point. So you could check it with the calculator. Have a look at it. What about at neg 3? Well, let's stick 3 back in the derived function. So it's 3 by 3 squared plus 4 by 3, take 15. So the slope is 24. So it should be very steep at 3 neg 13. Now again, you can draw the graph and have a look at what's happening there. And you can also use graph mode or math or linear mode in the run mode on the calculator to evaluate. Not only look at the graph, you can evaluate f dash x or dy by dx at those points from what we said before. Okay, let's have a look at part B. Part B is this function. 2x takes 7 all squared. So if we multiply that out, we get this function. First one squared, twice the product, second one squared. Let's do it term by term. Here we are. It's 4 lots of x squared, 28 lots of the derivative, and the derivative of 49. The derivative of x squared is 2x, times 4 is 8x. Derivative of x is 1, so it's neg 28 times 1. Derivative of a constant, 49, is 0. There is no rate of change, is there, of a constant? Remember, this is the slope of the tangent to the curve or the instantaneous rate of change. And if something is a constant, it's not changing as x changes. Let's just check that again. Let's just reinforce this graphically. So if we have y equals 49 somewhere up here, then you can say the slope of the tangent is 0. It's parallel to the x-axis. Or the rate of change of 49, remember the trichotomy I just did in that circle back there, the rate of change of 49 is 0. It doesn't change as x changes. It's forever the same. Okay, so we've got a final derivative of this function of 8x take 28. Let's now use it to evaluate the slope of the curve or the slope of the tangent. At 2, 9, you will put 2 in the function. So it's 8 by 2, take 28, neg 12. Let's put in 7 over 2 in place of x. It's 8 times 7 over 2, take 28. Slope of the tangent to the curve, or the slope of the curve itself if you like, is 0. That means it should be horizontal. Just remembering, if you look at any function, let's take a function here, and you say the slope of the tangent is 0, let's come down and make that touch there a bit. Slope is 0, the slope is 0. It's parallel to the x-axis, isn't it? So it's a horizontal tangent. That's what we're saying. A horizontal line has a slope of 0. Remember some of that old stuff now. Okay, what about this function? We've got to split it into 2 pieces. Oh, there we are. Do you remember your rational powers? Root of x is x to the half. And then derivative of 6. So it's 3 times derivative of x to the half. Use the x to the n rule. Let's put it over here and check it. If y equals x to the n, dy by dx is nx n minus 1. So what's that? Let's check it. It's a half. Here it is. A half x minus 1. A half take 1 is neg a half. Just check that. Getting confusing there. We'll just go back up there a little bit. So here, and the derivative then of 6 is 0. So it is 3, and there's a 2 on the bottom line, 3 over 2. X to the neg a half is 1 over x to the half. Getting complicated. So the derivative of our original function here is f dash x is 3 over 2x to the half, or 3 over 2 root x. Please remember, you've got to be able to handle this sign in terms of a rational power. It means x to the half. So root of x is equivalent to x to the half. And then negative powers. Negative powers mean 1 over. Okay, so let's work out the slope of the curve at the first point, 4 naught. So we'll put 4 in here. 3 over 2 root 4. 3 over 2 by 2, 3 over 4. Put in 9 in there. 3 over 2 root 9 a half. So are you getting the idea here that we can put in x values into our derivative or our derived function to get the slope of the tangent? So this is important. Because the slope at x equals 9 is only a half, and the slope at x equals 4 is steeper, we should observe the graph of the equation becoming less steep as we move along the curve from x equals 4 to x equals 9. This is using the idea of the slope of the tangent being, okay, if we got it 4, the slope is 3/4, so that's fairly steep, and at 9 it's less steep, isn't it? Or the rate of change. The function is climbing more rapidly at 4 than what it is at 9, by the slope of the tangent or the steepness of the graph. We want to try and move across now to understanding the full usefulness of this derivative, or the rate of change, or the slope of the tangent. Okay, what about this big one here? And then we'll finish and we'll try some. Here's a big function. A quarter of x to the fourth, so it's a quarter of the derivative of x to the fourth. 3 over 2, neg 3 over 2, times the derivative of x cubed. And then neg 2 by derivative of x squared. 15 over 2, just worrying about the x parts. Okay, derivative of x to the fourth is 4x cubed. 3 over 2 is constant out the front. Derivative of x cubed is 3x squared. Derivative of x squared is 2x. Derivative of x is only 1. Constant rate of change there. Okay, and derivative of 3/4 is 0. A constant does not have a rate of change. Or the slope of the tangent to the line y equals 3/4 is 0. It's parallel to the x-axis. So overall, if we simplify that, there we have the derived function, or the derivative, stated. And then we can put it here as f dash x. What that means is if we stick x as 5 in all the x holes here, we'll have the slope of the tangent at that point, and that will be 0. So that will be a flattening point again at x is equal to 5. So if we're starting to picture that out here at 5, whatever the function is doing, oops, come over here, that's 5, not that one, we'll cheat a little bit here. So here at x is equal to 5, it's a flattening point, isn't it? Because we've just shown, come back here, we've just shown that the slope of the tangent is 0. What that means is the tangent here is horizontal, so it's got some sort of turning point like that there. Okay, slope of the curve at 0, 0, stick 0 in the x holes up here, and we get 5 over 2. So can you see this is starting to have connections to graphing and understanding why a function might have a curved shape. Alright, I hope you're getting the hang of this. Let's go down and see if we can do some. First of all though, here's a comment. You can't use the graphics display calculator to find the function, but what can you do with the graphics display calculator? Well, one thing we've already found is you can find the value of f-x at any x value. We can't actually find the formula for f-x. Okay, but we can find the value of it at any x value. And we've done 3 ways. Right, run mode in math and linear form, and also graph mode. But what about this? I'll show you. Come to graph mode now. The second way in which the calculator can help you with the derivative is to say, well, let's graph the function. And this is in graph mode, so I've got 3 root x takes 6. And then if I hit over here, let's go and hit options, up comes this window again, and we can actually go to calc, which is F2 in graph mode, and up comes d by dx there. If we choose that with F1, here we've got it in y2 hole. Oh, sorry, I forgot to say, you've got to scroll down. Once you put the function in, scroll down so you've got F2 or y2 highlighted. Then choose that option. See what we've got here? In the y2 hole, we've got the option of finding the derivative. So now, if we hit F1 to choose y, and there it is, and then hit 1, we can put in there the second function is d by dx y1. So what that means here, we can graph both the function, there's the function there, oops, sorry, that's the function, this is 3 root x take 6, and that's the derivative of 3 root x take 6. So the calculator will actually draw the derivative for you. So if you've come up with a derivative from your rules or first principles, you could actually check whether the graph lies on top of the graph that the calculator will give you for the derivative. Unfortunately, the calculator cannot find dy by dx like that and give you a function in here, because it's not a CAS calculator, computer algebra systems calculator. It can't display the actual algebraic expression for the derivative, but it can draw the graph of the derivative. Okay, so that's an interesting thing to have up your sleeve. So are you getting the idea of all the ways of coming at this derivative? From first principles, remembering the derivative is the expression which gives you the slope of the tangent to the curve, or the instantaneous rate of change. You can find its value at any point for any curve. You can also graph it now. Here we are, graph it. But it will, the GDC will not give you the actual algebraic expression for that derivative. Okay, please keep in mind all these alternatives. They are handy, only in paper 2 though, where you've got a calculator on board. Okay, let's go down and have a look at some examples. Okay, here we have a curve. This is a little bit different. It's a mystery curve. It's got an a value missing there, and we're told it has a turning point where x is -2. Determine the value of a. Now, at a turning point there must be a horizontal tangent. Okay, now do we agree with that? A horizontal tangents have a slope of 0. Let's have a look at some graphs with turning points. Something like that. Turning around points. There's a maximum, there's a minimum. If you drew a tangent, can you see, oops, there, oops, we've missed the whole thing. So we'll just go back and do that again. So can you see that at those turning points, there and there, if I drew a tangent, it has to be horizontal. I've missed the point there again. So it's got to be horizontal there, through there like that. Okay, let's try and tidy it up a bit. It's hard on screen to do this. Okay, so that will be horizontal, and through here also. if I drew a tangent at any turning point, the slope would be 0. So these points are characterised by the derivative of the function being 0. So we can backtrack and find the formula for the function. Let's do it. So the derivative of the function is the derivative of this thing. Now a is a constant, it said, so it's a by the derivative of x cubed, 7 by the derivative of x squared, neg 8 times derivative of x, derivative of a constant. And if we simplify that, this is 3ax squared, remember the derivative of x cubed is 3x squared, a in front, derivative of x squared is 2x, so it's 14x, and the derivative of x is 1, so this is just neg 8, derivative of a constant is 0. Constant doesn't change with respect to x. Okay, so we know when x is neg 2, it's got a turning point. So when x is neg 2, let's put in neg 2 into our derivative function to find the slope of the tangent. So it's 3a by neg 2 squared plus 14 by neg 2, take 8, and that must be 0, because we are told that it's a turning point. And at a turning point of a function, the slope of the tangent would be 0. So let's put equal to 0. Hey, and we can backtrack now. That becomes, this expression becomes 12a, take 28, take 8, must be 0, a must be 3. And you could actually put that on your calculator now and draw the graph of that function and see if that agrees with the turning point at neg 2, and would the tangent be flat there? Would it be horizontal? Would it be parallel to the x-axis? So that's an interesting little tricky-do there, to use the derivative. Okay, let's look at some more now. Example 10 here. Boiling water is poured into a cup. Okay. The temperature of the water in degrees Celsius is given, that's an interesting formula there. Given by that where t is in minutes greater than or equal to 1 minute. Find the, look out, watch this, average rate of change. Okay, well let's draw the graph of that. And if you use your calculator to draw the graph of that, you get this function. And the average rate of change, remember, you take it at t equals 2 and t equals 6. And the average rate is the slope of the chord, not the derivative stuff, not calculus. That's what led Newton, also Leibniz, to develop calculus and to discover calculus, because they didn't want the average from one point to the other. But here, that's what we're being asked for. So come on down, let's just have a look at this. So let's work out when t is 2, let's stick t is 2 in the formula and get the Celsius degrees at A3.5, and it's t is 6, let's put it in there and get the Celsius temperature 31.38. So, can we find the average rate of change? This is the slope of the chord between those 2 points. So let's do it. Y step over x step. So 83.35, take 31.38, there it is. 2, take 6. Y step on x step. So this is negative 12.9925. Well, that agrees, because see this chord? It's got a negative slope, hasn't it, moving that way. As x increases, or t increases, as t increases, c decreases. So it is a negative rate of change. So we would say, let's go 3 significant figures, it'd be neg 13.0 degrees Celsius per minute. A rate of change, how one variable changes with respect to the other. And then interpreting it, every minute that goes by we expect a drop of about 13 degrees as an average between those 2 points. But that's not what we're interested in, were we? We're interested in calculus. So let's have a look at doing calculus on this. let's find the rate of change exactly at the moment when t is 4. This is Newton's dilemma, isn't it? Newton again with v inst. Don't want it between 2 points. I want it at a particular time point. So let's do the derivative, which gives you the instantaneous rate of change, or the slope of the tangent. Let's change the function to a power, because we have a rule for that. 182 over t to the 3 on 2, 182t to the neg 3 on 2. So the derivative of a constant is 0, and then we want the derivative of this creature. So 0 plus constant out the front. This is the x to the n rule, isn't it? Remember, if you've got y equals x to the n, the derivative is nx n minus 1, even if it's a fraction. So it's neg 3 over 2, t, neg 3 over 2, take 1, neg 5 over 2. Right? Two negatives there. Neg 1.5, take 1. It's neg 2.5 if you like. So there's our derivative. Look at the notation. Not in y and x land now, but we've got to keep it in context. The variables are not y and x, they are degrees Celsius and time. So now let's put 4 in, and if you put 4 in here, we've got this expression, and we can work that out, the square root of 4 to the 5th. Let's do the root of 4 first, which is 2. Raise it to the 5th is 32, which is neg 8.53. What does that mean? It means that t equals 4 at that instant in time, the rate of change is neg 8.53 degrees Celsius per minute. Okay, let's come down and have a look. Oh yes, and that would be the slope of the tangent. There it is. Draw the tangent at that point. At that particular instant, right at t is 4, that is how the degrees Celsius is changing with time. Are you getting the hang of this? We can get some quite complicated algebraic expressions though, can't we? With these t to the 3 over 2s and things like that. But that's what in the real world mathematics is most valuable for. It can model and explain natural phenomenon, scientific phenomenon, if you are prepared to work with more difficult numbers. Okay, let's go on now and have a look at, I've taken an example here, and some problems I want you to try from Hayes and Harris, another publisher, and let's look at going through the process very slowly. Fine, and here you are, first principles keyword, the slope function for this. Well, that's a function which gives you the slope of the tangent or the instantaneous rate of change. So you always set it out with f dash x equals the definition. Then x squared is our function, so into the function in place of x you put x plus 8. So it's x plus 8 squared, putting x plus 8 in place of the variable there, minus x squared, expanding it, we've seen this one before, and then subtracting, and then cancelling. I like provided that, the proviso, that h is not equal to 0 for either of those, and then as h tends to 0, what's left? This thing. So if you make that tend to 0, the function will tend to 2x. So your derived function is 2x. This little dude will give you the slope of the tangent, 2x squared, at any x value. Slope of the tangent to f of x equals x squared at any value, or the instantaneous rate of change of x squared at any x value. So here are some hints here. In question 1, they want you to try and do this rule for these functions, and in the IB syllabus they say you have to use this first principles for simple polynomials. So we're only going to do simple polynomials. Remember, you might need to be able to expand powers of a binomial. Why? Because the definition has got, come back up here, it's got f of x plus h in it. So x plus h to any power is going to give you binomials here down the bottom. So here are some more. 2x plus 5, x squared take 3x, and x cubed take 2x squared plus 3. So I want you to try to go through that process of first principles differentiation, or finding the derivative from first principles. Set it out like that and see how you go. Alright, underneath here I've got the solutions to each of these. So pause the presentation, have a go, and then fast forward as you've done one and check your answers now. Okay, so I think I can get them all on one page. Yes, there we have all of them. So just remembering, it's going to be important that if you've got x cubed over here, you can expand it. X to the fourth. This is part of the course. It's the binomial expansion, so you might have to go back and review that. Alright, have a go. I want to move on to Pearson's exercises now. So let's go down now and have a look. So here in 11.2 from Pearson's, find the derivative of the function by applying the limit definition. This is called, remember, usually first principles, not so much the limit definition, but it's called the first principles differentiation process. So we'll try those problems there. And then using your results, find the slope of each of the graph of each function when x is 1. And then sketch the function. You might use a calculator to help you there. And draw in a line which represents a tangent to the graph at x equals 1. Just consolidating that you know what's going on there. Okay, question 6 to 12. Find the derivative and find the slope of the graph at the indicated point. Use a calculator to confirm your results. I won't show that in the answers. So you do the process. Now find the derivative of a function. No one says from first principles. So use a rule. You only use the first principles method if they make you, if they tell you to. Otherwise, use a rule and substitute in the x value from the point to find the slope of the graph or the slope of the tangent. Okay, come down there and we'll have a look at these 6 to 12. Oh, there we are. I have a go at those. And then 13. This is similar to the problem we did, a little bit harder, because you have to actually sub in the x and the y value from here, as well as putting the derivative equal to 0 at x equals neg 1. Let's go to 14 to 17. There we are, 14 to 17. Okay, use your head a bit around those. Let's have a look at 18. Use the graph to answer each of the questions in 18. Let's have a look at 19. Go to, can we get through? I will get 19 through to 23. Okay, some tricky ones there. We'll have to look at those. Okay, let's have a look at 24. I think that's the last one then. 24. Alright, now let's look at the answers to these and see what you think. Okay, 1 to 3. All the algebra stuff there. Let's look at question 4. 4 and 5. Let's look at the rest of 5, part 2 and 3. And part 4. Okay, drawing a picture helps, doesn't it? And then question 6, 6, 7 and 8. I haven't put in the graphics display calculator check there. You can do that for yourself. Okay, 9 and 10. Can we get on 11? Yep. 9, 10, 11. Twelve and 13. 14 and 15. We've got 16 now. 16 and 17. Let's look at that graph one. 18. Okay, let's look at 19 now. 19 and 20. '21 and 22. Look at 23. Oh, we've got them all on there, 23 and 24. So, gee, it's moved along quickly, hasn't it? It really has, and you're now quite powerful, but you might have to go back and have a look at the presentation again to make sure you understand all that's going on. Because now we're able to find the derivative, which is the rate of change of the function, or the slope of the tangent, for a whole lot of functions now, without drawing tangents themselves and trying to estimate the slope with the error involved in that sort of construction. We now have some rules, some algebra. That's exciting. All right, well, we're going to leave it there, and we're going to have a number of other presentations to build on the usefulness of what we've found here. But for the moment, it's cheers from me.